Sasha, and thank you to Daniela and Pulami for organizing the seminars. I think everyone can agree it's nice to have some motivation. We haven't seen each other much in person this year, and yeah. So today, so for those of you who don't know, I think I've pretty much met everybody here now, but I'm Elodie. I started a postdoc here in November last year. And today I'm going to be talking to you about realistic models of plate tectonic evolution in aspect. And I'm working with Stefan, Sasha, Anna, Frederic, and also CJ as part of the MEET project. So what I'm presenting today, I'm putting into a poster for AGU next week. So this work is not close to being published, but I thought it would be good to start a discussion and to show you the kind of models that are being built in aspect and the kind of issues and solutions we found along the way. Okay, so as most of you know, we still don't have a consensus about when and how plate tectonics started and what controls its evolution. And this is primarily because ancient rocks are very rare and altered. And so we have a relatively poor knowledge of crustal and mantle evolution with time, and particularly in the Hadean and the Archean. But this really limits progress in constraining, for example, the origin and the evolution of the continents, oceans, and life. So if we look at this figure from Sobolev and Brown, 2019, we can see that in the Hadean and the Archean, we think there was no global plate tectonics as we know today, and instead potentially a squishy lid regime and or retreating subduction zones. After this period, it's thought there's intermittent plate tectonics. So by these blue arrows, we see major glaciation events. And in the green rectangles, we see potential major lubrication events. And these are inferred from sediment proxies. So for example, this dashed blue line represents the strontian isotope in seawater. So telling you about the continental sediments in the seawater. And we can see these peaks immediately after the glaciation events. So in this region, did someone say something? Oh, okay. Okay. Oh, it's just a feedback. Okay. So then we have this region of intermittent plate tectonics. And this region of the boring billion between 0.75 and 1.75 billion years ago, where plate speed was thought to be very slow and plate tectonics was very sluggish. Then we have the snowball earth glaciation, and immediately after, again, we see this peak in the sediment proxy. And then we come to the continuous plate tectonics that we know today. So today I'm going to be focusing on some present day convection models, but our aim is to go back at least to 2 billion years and look at this really these shifts in the dynamics. And so it's been proposed since quite a while that unconsolidated sediments in the trenches can serve as an efficient lubricant for subduction. And so the underlying hypothesis of this project are that the accumulation of continental sediments in the trenches played a crucial role during the evolution of plate tectonics and may have even aided in its initiation. And also we want to know what the conditions were like at the beginning and end of the boring billion with this kind of sluggish plate tectonics. And so in order to answer these questions and many others, Stefan and his co-PIs were awarded the ERC Grant in 2019 called Monitoring Earth's Evolution Through Time. So most of you know it as MEET. And what I'm showing you here is this triangle between us in the geodynamic modeling section. So my focus on mantle convection and plate tectonics, and CJ looking at crustal production and recycling, and then how we pass our constraints to the geochemists and receive also some of their data. So they're looking at the evolution of mantle and crustal composition from a wide range of data. And so I'm building dynamical global mantle convection models for the first time with Aspect. So as most of you know, because most of you are using it, it's an open source community code, finite element code, which is becoming much more popular in the field. And the reason why we chose this code over some of the other maybe more developed codes is that we can model a free surface, and we can also have adaptive mesh refinement. So this is going to be really useful when we want to model, look at the effect of sediments in trenches, and combining tectonic and erosional routines. So I've been developing 2D visco-plastic spherical shell models with just this typical Arrhenius viscosity law, which depends on pressure and temperature. For now, we've just been using simpler diffusion rheology, and obviously this Drucker-Prager plasticity. So the yield stress depends on cohesion, friction, and pressure. And so this first year has really been an installation phase because some of the features were either not in Aspect or they didn't kind of work together. And the most important part to get these models to converge is the very initial stages where these plumes are forming self-consistently and rising with velocities of meters per year and breaking the slab, breaking the lid, and this is quite difficult for the solvers. So here I'm showing you temperature, density, viscosity, and velocity, and I'm going to talk you through the initial conditions of the model I'm presenting today. So we have a typical surface, an adiabatic temperature, surface temperature for present day, 100 million year old lithosphere, radiogenic heating, and obviously a core mantle boundary temperature. We have a typical phase transition at the 410 and the 660, and our models are fully compressible, so thermal expansivity and density and so on vary with depth. Our viscosity, as I said, is temperature and pressure dependent, and we use a dry rheology following Siskova et al. 2012. We have a free slip boundary on the core mantle boundary and the surface, so no tangential shear stresses on those boundaries. And so here I'm showing you the refinement in our models. So here on the global scale and a zoom in on the right. So this model is at refinement level total 8, but we have also been going up to 10. So here the resolution in the radial direction is 5 kilometers in the top and bottom 200 kilometers, decreasing to 11 kilometers down to 700, and then around 45 kilometers in the middle of the domain. Here I'm showing you viscosity, so depth with the log of viscosity, and you can see our profile here in green is somewhere in between the profiles of Siskova et al. 2012 in pink, and also Steinberger and Calderwood in 2006 in this red line here. So we've actually set the minimum viscosity to 10 to the 20 and the maximum to 10 to the 24 because we are struggling with convergence if we increase this range. And after solving 1, 2, 3, quite a few issues with Aspect and making some pull requests so that it's going to help the others in the community, I can now present the present day model that we have right now. So let's see how plate tectonics may have changed with varying sediment influx in these very simplified models. So we can do this, we can have a proxy for changing sediment influx by changing the plastic parameters. So again, this I remind you that the yield strength or stress depends on the cohesion, friction, and pressure. But we can start by just varying the cohesion as a proxy. And so these models run with 2 million degrees of freedom on 66 cores, and it took around 15 days to get to the end of the 2 billion years that I ran these models for. And so what I'm showing you here on the left and on the right, so it's the same model with cohesion or yield stress, 40 megapascal. And I run these models to 1 billion years. So we already see some quite stable subduction zones, some realistic plumes coming up. And then at 1 billion years, I switched the cohesion from 40 to 60 megapascal. So this would represent a decrease in sediments in the trenches. And so you can see until this point, we don't see any big differences. But as we head towards 1.2 billion years, for example, here, if I just stop, this plume and, for example, this plume here was able to break the lid with yield stress 40, but not with cohesion or yield stress 60. So the lid is too strong on the right. And we can see, so we obviously see we can form less new subduction zones. And then at 1.5 billion years, I'm going to switch the yield stress or cohesion down from 60 to 20. And this would reflect an increase in the amount of sediments in the trenches. And we're going to see how it changes the dynamics. And so immediately you see the plumes are much more able to break the lid. We see many more subduction zones. And we see much more material going down into the lower mantle. And so let's just pause on one or two of these screenshots. So here is at 1.3 or so billion years. And let's see if we can try to correlate these different dynamics with possible events in Earth's history. So this increased yield stress could reflect the time around the boring billion. So between glaciation events where there were less sediments, higher friction at the trenches, and we can't see it here, but we have subduction zones that die out and new subduction zones that can't form. On the other hand, for a lower yield stress, this could represent a period in time after a glaciation event, so more sediments in the trenches, lower friction, and much more active subduction. And so let's have a little look at the data. So this is a figure from Stefan, and we're looking on the top at sediment proxies from the Neoproterozoic to present day. So in purple, you see the delta 18 oxygen isotope in the zircons, so in the magma that makes up the continental crust. And in blue, you can see there's again the strontium isotope that we've seen before, so a proxy for continental sediments in the seawater. And what we can see is, so we have the snowball Earth glaciation indicated in blue here. And ever after this glaciation, we see the increase in the sediment proxies to a peak around 500 million years ago, and then this steady decrease. Now in the bottom, we're plotting RMS continental plate speed for the same time period. So this is combining palaeomagnetic reconstructions from Meredith et al. And Torsvik and Cox. So you can see prior to the snowball Earth glaciations, the RMS plate speeds are roughly 5 centimeters per year. And then after the glaciations and some kind of intermediate lubrication time, the RMS velocity jumps from 5 to 15 centimeters per year. And then again, correlates very well with the sediment proxies and decreases to present day. So let's have a little look at predicted RMS velocities from our models and see how they compare. We can't compare exactly because we're running present day models into the future, but just to get an idea of how changing the yield stress correlates with changing RMS velocity. And so in the red dashed line, we see that reference model of cohesion or yield stress 40, and we see it gradually decreasing with time as our models are cooling. And in the blue line, we see this model which switches from cohesion 40 to cohesion 60 at 1 billion years. And so immediately we see this kind of lag, this shift in the plate speeds as we increase the yield strength. And then we see just a decrease in the plate speeds for the higher yield strength or having less sediments in the trenches. And then here on the right-hand side, after 1.5 billion years, as we decrease the strength of the lid to reflect having more sediments in the subduction zones, we see much more extreme variations compared to the reference model. This is as the new subduction zones are forming. So what we see is, in this case, an increase of only around 2-3 centimeters per year as we change this yield strength from 60 to 20. So this is much, much lower than the observations, which are around 10 centimeters per year. So we've also been playing with reducing the yield stress down to 10 megapascal. So again, on the bottom, you can see RMS velocity with time with this new model again in blue. So now we can see a jump in the RMS velocity from 2 to 9, which is a little bit more realistic, but we can see the full lid collapsing, which is not so realistic. And so something to bear in mind is that we're changing the strength of the entire lid, and with it should really only occur at the convergent plate boundaries. And also we make this switch very quickly, and this switch in yield stress should probably be more continuous, and we can start to begin to look at the effects of that. Something else to bear in mind is there could be some positive feedback here. So the more sediments you have in the trenches, the faster and the more active and more subduction you have, the more mountain belts you have, and this feeds back into the loop. And so here I'm plotting subduction zones versus time for, again, this reference model in the red dashed line, and the model going as we increase the yield strength and then decrease the yield strength. So here we can see that as we increase the yield strength, again, we lose one of the subduction zones and we're unable to form new subduction zones if we have less sediments in the trenches. And on the right-hand side, we can see as we decrease the yield strength, or as a proxy for having more sediments in the trenches, we actually double the amount of subduction zones in the model. So what does this mean in terms of heat flow? So here I'm plotting surface conductive heat flow with time. And obviously, if we have a higher yield strength and less subduction zones, we have substantially lower surface conductive heat flow, and vice versa for the model with a lower yield strength. Something else to note is that we don't see a big difference in the core mantle boundary heat flow when we increase the strength of the lid, but on decreasing the strength of the lid, we see quite a substantial decrease in CMB heat flow as more subduction zones feed more material down into the lower mantle and kind of insulate the CMB. So in conclusion, for the first time, we've developed these fully dynamical 2D global mantle convection models in aspect. An increase in yield strength of the lithosphere as a proxy for low sediment supply in the trenches, such as during the boring billion, leads to less active subduction zones and slower plate speeds. And on the other hand, a decrease in the yield stress of the lithosphere as a proxy for high sediment supply in the trenches such as during the glaciation events, after the glaciation events, leads to much more active subduction zones and higher plate speeds. And so finally, I'm going to discuss the future work, which we've been trying to include a lot of these features for a while, and maybe some of you have also had some issues with these things, but always good to discuss them. So we're trying to go back to temperatures of 2 billion years ago. So it's only around 100 Kelvin difference. And we're also trying to increase our viscosity range from 20 to 24, increasing that, which is proving very difficult for convergence, even with a low CFL number and very high resolution. So there could be something else in the background that needs fixing. But we've been looking at using some of the better solvers, the defect correction Stokes, the Newton solver, the GMG solver, which we're not working with compressibility or null space removal, but I think we're close to getting there now. Obviously, we'd like to use friction instead of cohesion, and also get the free surface back, which has caused us a lot of issues, a lot of convergence problems, including dislocation creep, especially having a yield stress that depends on plate boundary, adding the continents, and finally, a little bit further into the future, starting to couple these tectonic models with a surface erosion routines such as Vascape. So a lot to do, but making progress for the first time with these models in Aspect. So thank you for your attention, and I'll take any questions.